Hi, I'm Ben. I'm a PhD student in the Klausberger lab based in Vienna, and I work on decision confidence in the orbitofrontal cortex. And I'm originally from London, the UK. We're going to go through polynomial regression and hopefully understand how to build a design matrix. So why would we want to do polynomial regression? So let's say we've tried the multiple linear regression, and for whatever reason, it's not working. We're not getting an effective prediction. It's possible that maybe we don't have the right data, the right features to predict our response. But it's also possible that there's a more complex relationship than the linear relationship. And we've only tried linear relationship between our features so far. So it's very possible that there is a non-linear relationship, and that's something certainly worth trying, which is one of many options available to you. So it's very similar to the linear regression case. Intercept, noise, theta times your feature. But then you've also got this expanded new terms, which is your a new theta new theta, and then x squared. So it's just your feature squared or your feature cubed. So it's very similar to the previous case, but now these nonlinear terms are involved. And the order of this polynomial regression is just the highest power. So x cubed in this case, this makes us a third order polynomial regression, but you could also imagine adding theta 4 x to the power of 4, and that would be fourth order. So we want to build a design matrix. We've got some example data that we've been given. We want to this feature here. We want to then get the relationship for our response. So we need to build a design matrix, much like we did before the multiple linear regression. So it's pretty much identical to the previous case, except for we now have these extra terms that I just described. So we've got each row representing an observation. So for example, trials, and then each column representing the feature. So then you also have, so first column ones, second column your feature, then the third column is feature cubed, feature to the power of 4. So we want to build that design matrix. So we've been asked for coding exercise 2.1, create a function, make design matrix, which takes in our data vector, our feature, and just gives us exactly what I just said, this design matrix based on a defined order. So the first step that we're going to need to do here is to comment out this raised error, which is in all the exercises. And then some of the work's been done for us. So we've already got X put into a columns, because right now it's just an ND array, which doesn't have, it could be a column, could be a row. So you got to tell Python that this is a column vector. And that does that for us. And then we've got this the column vector of ones. So those have already been built for us. So let's we want to stick them together, horizontally stack, matches our hint, NP stack. Great. So let's do NP stack. So stack takes in a single input, which is a tuple, and it horizontally stacks them. So the first thing in our design matrix is our column of ones. So let's start with that. And then we want to combine that with our X, which is now a column vector. But we don't want to stop there. We want to have increasing powers as we go. So we've got this loop to go through, and it will start out with a 1, degree 1, which will just give us the X. And then on the second iteration, it will give us X squared and X cubed, and so on and so forth. So need to correct that because it needs to be a tuple. And then we have some example that we know the answer to. So let's run that and see if we get the answer that we're expecting. So the order is 5 in this case. There's some kind of error. What do we need to look at? I've spelled this wrong. I've missed that is H stack typo. Great, fantastic. We have the answer. Great. So that matches. Let me know if you've got any questions. Yeah, thanks for your time.